Okay, so let's look at this quick list of numbers here as our warm-up. To start, this is a very famous pattern that you might notice it, and these are numbers all came from somewhere special. How did I get 1? Well, 1 times 1. How did I get 2? Or 4? 2 times 2. 9 is 3 times 3. 16 is 4 times 4, or this is the list of perfect squares. So then the next number would go 5, 6, 7, and we would square them all very quickly. And this list can keep on moving as far as we need it to. This is the list of the perfect squares. So now, what about the next sequence? How did we get the next sequence? Well, there's a little bit of a trick, and I wanted to connect it back to this list of perfect squares. This pattern here is basically present in this case, but it's present by one small piece. How did we get 3? Well, 3 is 3 times 1. How do I get 12? 12 is 3 times 4, but if we think of writing 4 a little more creatively, it's 2 squared. So what about 27? Well, 27 ends up being 3 squared, which, yes, this could be written as 3 cubed, but there's a reason why I want this 3 to be written. And then 3 times 16, or 3 times 4 squared. So this is a list of a special patterns that what we're doing is we're taking the perfect square numbers and we're timesing them by 3. So then I get 3 times 25 is 75. 3 times 36 is 108. And 3 times 49 is 147. So what I'd like to show you is that these numbers can be just, this pattern of perfect squares could just be multiplied by the same constant. It's times by 3, and it generates a whole new list of numbers that sometimes might be hard to recognize. All right. Quick little piece here. Positive attitude may not solve all your problems, but it will annoy enough people to make it worth the effort. All right. So here's what we got. I just allowed you to view the results from your Chapter 4 test, your Unit 4 test. I graded those. I can't remember if it was Monday night, Tuesday night, but I went through and graded those. And I want to share with you how I did the grading so you're just aware of what is going on. So anything that was worth 3 or 4 points, I went through and I looked to see if you had an educated answer because some of the distractors on the multiple choice questions were put in there to purposely trick you, but if you answered that, you still got 1 out of the 3 points or 1 out of the 4 points. So I kind of gave partial credit because I kind of knew your thinking. We made the mistake of not having you guys submit your work this time, and in the future we're gonna have you submit your work for every test because then we get to see the work and it's easier to justify rewarding points back on an incorrect answer. Um, but anyways, so you can now review your results, which means if your score was below 70%, you can do corrections on a separate sheet of paper for every problem that you got wrong. You have to show all your work. If there's a picture, you need to draw the picture. If you got something wrong in the proof, you need to write out the full 2-column proof with all the statements, all the reasons, and include the picture and put markings in the picture if there's vertical angles or alternate interior. And if you do that, I will give you 70% of your original score. So you could boost your grade up to a 70%. All right. Now, that has to be done soon. Um, and all you have to do then is email me that picture of your work, and I'll go and double check, compare that to your original test. And if everything works out, then I'll boost your score up to a 70%. I would like this to be due. Let me see if I can type. Due by Wednesday next week. I don't want this hanging over our head. and it's November. That date is the 11th. Don't put it off. You should be doing that this weekend if it didn't go your way. Now, you were able to do that for every unit test that we've had, which means you should, at bare minimum, you should be at a 70% for your tests. Um, Homework. If you have missing work, you need to get that in. That is also, homework and tests are worth basically the same amount in our grades. They're both 50% of the overall grade. So if you haven't been doing any homework, your grade is really low. If you haven't been doing any, if you haven't done any corrections on the test, your grade is probably really low. You got to balance both of those and improve that, so you can. All right. So some people are asking about the last question on the test. I can't go over that yet. And the reason why is I've got 5 or 6 people who have not taken the test yet, and they need to take that test before I can address problems publicly to the whole class. So if you would like to go over that question, we could talk about it in my office hours. The only thing I can kind of tell you is people didn't compare the full triangles. They compared a piece to a piece instead of a full length to a full length. And my hint would be, the only hint I'll give you is if you draw the 2 separate triangles, one for the bigger triangle and one for the smaller one, you're going to notice where your error was in that problem. So that's all I can say right now about it. Okay, this is really big, and I need everybody to listen right now. We only have 14 days left of the trimester if you count today. And a couple of those are going to be review and test days, so we don't have a lot of time left. You can think of it as about 2 weeks, 2 full weeks of school left. How do you improve your current grade? Well, can you do test corrections from any one of the unit tests? That's just opening it up, correcting it, emailing it to me, and you'll get 70%. All right. Now, did you do the Unit 3 proof project? That should have been the easiest points we had all year long. It was 50-point summative, and it was based off of Can Figure It. And then do you have any missing assignments or quizzes that you complete? All of this should be taken care of very soon if you want to improve your grade. So I just want to show you our schedule so you can see what's left and what we have going on. We are right here today. We're going to learn Pythagorean theorem and the converse. And then we have special right triangles, SOHCAHTOA, and a review of more trig. And then we've got a quiz, a review, and then the last 2 days before Thanksgiving break. This is the end of the trimester. So if you think of the times that we'll meet, we're going to meet today. We'll meet 1, 2, 3, 4, 5 more times after today. We're going to meet, and that's it, and we're done. So you really need to, if you want to improve your grade, you got to make some decisions and choices right now. Okay. I'll be available from 1 to 2 o'clock in my office hours if you have any questions, and I can kind of help you make a plan to get back on track. Um, Really quick, I just want to mention if you feel like, because I've had this conversation with a few people already, if you feel like accelerated geometry is moving too fast and you think you need to move to regular geometry, please let me know and we can get that conversation started and talk to counselors and make the move back for second trimester. If this class is too difficult or too fast, we want to make sure you're in the right place so you can be successful with mathematics. And sometimes it's just slowing down and taking another look at things. All right, so we are going to teach a skill here that you hopefully have learned in the past, but have found that it's hit and miss. Some students don't have this down, and some students really do. So we're going to talk about reducing radicals. Definitely write this one down. And this is where our warm-up comes into play. I want to find numbers that go into the 72, the 192, or 3 times 18. I want to find numbers that go into there that are perfect squares. So hopefully you're feeling comfortable on where this list of perfect squares come from. I like to write it out. So 1 squared, 2 squared, 3 squared, 4 squared, 5, 6, 7 squared is 49. 8 squared is 64. 9 squared, 10 squared, 11 squared, 12 squared, and then it could just keep on going. We usually don't go higher than 12. But this is the list of numbers that we want to see. What is the largest perfect square that divides into the number that's under the square root? So I'm gonna, you'll kind of get the hang of this, but it takes some practice. So our goal is to reduce what's under the square root. Well, to do that, I'm going to split up 72 as two different products. And I want to pick the largest number that goes into it. Now, what I would do, yep, 36. Alan got it. 36 goes right into 72 two times. Notice how I wrote this. 2 times 36 is 72. You can split radicals up underneath their own square root. And the benefit to doing that, I always try to write the perfect square first, is you know what that answer is. What is the square root of 36? It's just 6. And then the square root of 2, we actually can't write any further. It doesn't break down. So we reduced the square root of 72 into 6 times the square root of 2. It's like we're taking the perfect square factor out and then taking the square root of that. So what if it's a little harder to just picture it? Now this one you might see it right away. What is the largest perfect square that goes into 192? Here's my hint. Let's start with big numbers. Okay, does 100 divide evenly into 192? No. So then I'm going to go to the next one. Does 81 go into 192? And if you have a calculator and you need it, take 192 divided by 81. Now that doesn't go in evenly. So if that doesn't work, then let's go to 64 and take 64 divided by 192, or 192 divided by 64. And you can see that 64 times 3 gives me 192. And the reason why we want to pick the largest perfect square is the 3 has no other factors that are in this list. So the 3 is already broken down. And then we know that the square root of 64 is 8. So I get 8 square roots of 3. Now, you don't have to write this, but what if you didn't pick the largest perfect square? What if you said that, let me show you just quick. What if you were like, ooh, well, I know 4 and 48 go into it. Okay, cool. We know the square root of 48 is going to be 2, right? But that just means you have to keep looking at what's left over. Oh, wait a minute. Doesn't 4 go into 48? Yeah, so then that means I have another 2. Now, this is the long way to do it. You'll see why picking 64 is better. But then, oh, wait a minute, 12. Doesn't 4 also go into 12? Yeah, 4 goes into 12 3 times. So now it looks kind of messy and it looks like a lot of work, but I have a 2 times a 2 times a 2, and then I've got the square root of 3 left over. Well, wait a minute. What is 2 times 2 times 2? It's 8. So you can see that you're going to get the same work or same answer if you do it the long way. But 2 times 2 times 2 ends up being 8 square roots of 3. So since we knew 8 squared was 64, 64 was the better option to pick versus breaking it down the long way. Well, there's nothing wrong with doing a little extra work if you know you're going to get the right answer. Okay, now we have two problems here. There's two ways to approach a problem like this. If I have 3 times the square root of 18, well, I could leave the square root of 3 as is because there are no perfect squares other than 1. And we really don't use 1 because 1 goes into every number, and then I'm just left with the number itself. So that doesn't help, but 18 is really 9 times 2. And then when we do this, we end up with the square root of 9, and we know what the square root of 9 is. Square root of 9 ends up being 3. And then we would write the square roots together. So the square root of 3 comes down, square root of 2, but wait a minute, if it's underneath the square root, 3 times 2 gives me 6. So this is one way to do it. Another way is, what if I put the 3 and 18 together right away? So 3 times 18, and I keep them under their own square root. Well, 3 times 18, that's, what is that, 48, I think? I'm trying to, no, 54. I was way off. So now I want to look and see, well, what is a perfect square number that goes into 54? 9. 9 times 6 is 54. So if I split the square root up, I get the square root of 9, which is 3, and the 6 doesn't break down evenly because no perfect squares go into it. And notice, we got the same answer. So there often are more than one way to reduce these, and it's how you think of it. Some of them are really quick work. Some of them are long, keep breaking it down and breaking it down. But you should always check with the number that's under the square root in your answer and say, can that part be broken down any further? Okay, we're going to be doing this with our answers today, so you'll get a lot of practice with this. I don't want you to write this. I want to show you something really quick. So do not write this, and we're not going to spend a lot of time on it. It's just, I want to make sure you guys know there's a difference between multiplying radicals and adding radicals. So look at this. We talked about this before, that if you have 4 times 9, that's the same thing as the square root of 36. Right? 4 times 9 is a square root, so you can multiply them together, and the square root of 36 is 6. Or, if I wanted to, I could do it a different way. The square root of 4 is 2. The square root of 9 is 3, and notice I get the same answer. So cool, that works when you have square roots. But what about when you don't? Like 18, that's not a perfect square root, but 2 times 18 is 36, and that's equal to, that's equal to 6. But what if we did it the other way? I wanted to do that in orange, sorry. So we get 2 times 18 is 36, square root of 36 is 6. So what about the other way? Well, I can't break down 2, but isn't 18 just the square root of 9 times the square root of 2? And then what is the square root of 9? The square root of 9 is 3. And then I have the square root of 2 times the square root of 2, which is really the square root of 4. And the square root of 4 is 2. So you can kind of see we're getting at the same answer if it's friendly enough. And sometimes it's easier to go straight across and multiply. Sometimes it's easier to quick break it down. It just depends on the problem. So this one, same thing. 3 times 12 is 36. Square root of 36 is 6. But 12 can be rewritten as the square root of 4 times the square root of 3, which is 2. And then this original square root of 3 is just going to drop down. And now I have a square root of 3 times the square root of 3, which is the square root of 9. But isn't the square root of 9 just 3? And 2 times 3 is 6. So all of the answers are kind of the same for the first one, which is just coincidence. But it doesn't work that way with subtraction. Now let's look at this, or subtraction or addition. So square root of 4 times the square root of 9 is not the square root of 13. Okay, and I want you to be well aware, you cannot add kind of with that same thought process of how we did multiplication. So here's what I got. We know the square root of 4 is 2. And we know the square root of 9 is 3. And 2 plus 3 is equal to 5. So notice you cannot add radicals the same way. The square root of 13 is, if you check it in your phone or calculator, the square root of 14 is less than the square root of 16. The square root of 16 is 4. So I'm thinking this is like 3 point something. I'm just going to double check here. 3.601. That's roughly what it's equal to. It's not equal to 5. So there's proof that you cannot just add those together. So how do we add radicals if they don't break down into perfect squares? Well, we have to have the same radical. And I'm going to just kind of use this. We know the square root of 18 turned into square root of 9 times the square root of 2, which is 3 square roots of 2. So now here's how we add these together. I have 1 square root of 2 and I have 3 square roots of 2. So how many total square roots of 2 do I have? I've got 4. Okay, and then same thing here. We know what the square root of 12 is. The square root of 12 turned into 2 square roots of 3 from above. So here I have 2 square roots of 3, and I'm adding it. You can always put a 1 in front. So here I have 1 square root of 3, and I'm adding it to 2 square roots of 3. So now I have 3 square roots of 3. All right, so that was just a little piece that we're not going to do a lot with adding. I don't think we're going to do anything with adding, but I just didn't want you to think that multiplication and addition kind of worked the same way with radicals. All right, so we're going to jump into this. Let me just quick check. Okay, I don't want you to write this first page other than the title. We're starting Unit 5, and I will say Unit 5 is probably the absolute most important unit that we are going to learn this year. It is the one that you will use in pretty much every day of your math career from here on out, because it's going to do Pythagorean theorem, special right triangles, and trigonometry. And you might not know what all of those are yet, but those skills are used in pre-calculus, they're used in algebra 2, and they're used very often in calculus. So please put all of your energy and focus into this unit. Some of you that are feeling like I might be stuck or I might be way behind, this is your chance. It's a lot of algebra, and you don't need a lot of geometry knowledge to be super successful with this piece. So hopefully that's going to be buy-in for us to kind of really do well in this unit, because it's going to set your path for the next couple years. All right, don't write this. This is just, we basically already know the Pythagorean theorem. I want to just double check and confirm, and we already talked about this, is you guys all understand when we have a right triangle, the hypotenuse is always the longest side across from the right angle. All right, and then when we refer to the legs are the two lengths that actually make up the 90-degree triangle. So no need to write that. And it's up to you if you want to write this part right here. But we're going to officially define the Pythagorean theorem. And I'm going to ask that you write it in a very specific way. So in words, what is the Pythagorean theorem? It says in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the legs. Wait a minute. The square of the hypotenuse. Okay, well, if I'm going to call the hypotenuse C, and I'm going to call the legs A and B, and the Pythagorean theorem says that the square of the hypotenuse, so this length C, is equal to the other two sides squared. Now you're probably thinking, why did you write C squared first? Can't I write it on the other side? And you can, but I want you to write C squared on the left-handed side, because that's going to help us set up a little bit for things we're doing later on today. Now, this relationship, if the length of this number squared is equal to the length of the other two sides squared and added together, then that proves that this has to be a 90-degree angle. So this statement proves that we have a right triangle. All right, so we're going to jump past this because I hope we're already comfortable with the Pythagorean theorem. I want to show you two really quick visual proofs. It takes a couple seconds. So notice, I want to show you a algebraic proof. Do not write this. It's definitely not worth our time here, but I take that back. It's worth our time, but I don't think you need to follow along. And you will not be asked to recreate this. All right. This is just something that you're kind of watching for. And hopefully you will see that this relationship helps us develop a proof for the Pythagorean theorem. So I want to find the area of the big square. Well, a square, the area of a square is side length times side length. So what is the side length? It's A plus B. I like to write A plus B, and you'll see why. So what if I take A plus B and I square it? Well, squaring a binomial is the same as FOIL, right? So I'm going to distribute. A times A is A squared. A times B is AB. B times A can also be written as A times B, and B times B is B squared. And then I just have my two like terms in the middle. I've got AB and AB, which is really 2AB squared. So nothing crazy there. But then I have the area of all the pieces. So I got to find the area of each one of these small pieces and add them up. Well, wait a minute. This is a triangle, and the area of this triangle right here is base times height half. So it's 1/2 AB. That's the area of this blue triangle, but I've got 4 of them total. So the area of all the pieces is I have 4 areas of the triangles plus 1 area of that square, or some people like to say the diamond for C. Well, we just kind of quickly did the area of one of the triangles. That was 1/2 AB. And then I have the area of this square, which I should have put 90-degree marks in here. But this is just a C times C to figure out the area. That's C squared. So now let's simplify. 4 times 1/2 is 2AB plus C squared. Now notice, the area of the big shape is equal to the area of all the small pieces. So these two relationships are equal. But wait a minute. Don't they have something in common? They each have a 2AB. So if I subtract a 2AB from one side, they reduce out. And what's left over? A squared plus B squared equals C squared. We just algebraically proved the Pythagorean theorem. Okay, I do want you to write some of this. Okay, let's look at this part right here. We have something called the Pythagorean triple. And a triple is a set of numbers that satisfy the Pythagorean theorem. So I'm going to give you the first set. And The most famous set of Pythagorean numbers are 3, 4, 5. And what we have to do is we kind of just have to justify, does that 3, 4, 5 triangle actually create and satisfy the Pythagorean theorem? So if I set this up and I use the Pythagorean theorem, I just want to quick prove C has to be the longest side, the 90-degree angle. It doesn't matter which side is A and B then. I can pick whichever one. So let's plug this in just really quick, and you don't really even need to write this part down. I just want to show you that does 5 squared equal 3 squared plus 4 squared? Well, we saw in that video that 3 squares is 9, a 3 by 3 square, and a 4 by 4 square is 16. And when you add that up, you get 25 equals 25, which means this proves that 3, 4, 5 will always give me a right triangle. So I would like you to write this part right here. Common Pythagorean triples. These are 3 sets of numbers that satisfy the Pythagorean theorem. And if you are not positive, go ahead and check yourself. 5 is always, the largest side is always the hypotenuse. So you can always tell which is the largest side. This is the biggest number. And then if I did 5 squared plus 12 squared, does that equal 13 squared? Key is you have to square them, but yeah. So here's a set of 4 famous or common triples. Why is it important to know these? That's something to think about. Well, why? Cool. These numbers satisfy the Pythagorean theorem. Why is it important to know a 3, 4, 5 triangle? Or how about a 5, 12, 13 triangle? Well, look at this problem that I just kind of put here. What if I tell you that you absolutely know it's already a right triangle, and you know that one side is 8 and the longest side is 17? And if you've memorized this, you don't have to show any work. You automatically know that if I have A is 8 and C is 17, then the only number that could ever possibly exist is this side has to be 15, and you don't have to do any work. All right? So here's the nice thing about Pythagorean triples. If you recognize them, it reduces the amount of work you have to do by a significant amount. If you don't recognize it's a triple, you can still do all the algebra work and still get the same answer, and there's nothing lost. It just takes a little bit longer time. Okay. Here's one I want you to think of really quick. What if I give you this side length is 10, this side length is 24, and I want you to find x. Without doing any work, could you figure out what x is? Now, here's the thing I didn't share with you yet, but it's in the title. Not only are these triples satisfy the Pythagorean theorem, but so do their multiples. So what do we mean by that? Well, what if I multiply everything, the 3, 4, 5, by 2? That turns into 6, 8, 10. That is also going to satisfy the Pythagorean triples, or the Pythagorean theorem. I can multiply everything by 3. 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15. So any multiplier of x, where x can be any number, will result in a triple. So this is a triple that's disguised. And maybe you see it, maybe you don't, but look right here, 10, 24, 26. And notice the 26 is the largest number, so if you recognize it, you didn't have to show any work and you knew that that was a triple. All right, now I don't want you to write all these triples down because there's an infinite amount of lists because x can be any number. So I really wanted you to just get the 4 ones here, the 4 key ones. And I'll be honest with you, for some reason, I never recognize 8, 15, 17. I always forget about it until I do the work, and then I'm like, oh, that was a triple. I should have known that one. But 3, 4, 5, 5, 12, 13, and 7, 24, 25 somehow always stick in my brain. All right, so those are triples. You'll see as we do things how they come up and why it works. We're going to skip that slide, and now we're going to go here. And our job is to use this idea of Pythagorean theorems and maybe triples. I'm not saying triples always work because they don't. So we have to be careful. But here's a picture, and our job is to find the missing side lengths. So I'll give you a second to draw this. And we have to find the length of every side on this shape. Okay, so the congruent markings are key. Now, we don't officially know why yet because we haven't studied it, but I'm sure you can figure it out. We've got a rectangle. And because of linear pairs, this is 90 degrees as well. But I also know that if the height is 6, then the height is 6 of the triangle. If the length is 12, the length here is 12, and then the length of the leg of the triangle here is 12 as well. So I used my congruent markings to find the pieces, and now I've got an A, a B, and I got to find the hypotenuse, which is C. So I'm going to just use my relationship. And you might be thinking, ooh, is this a triple? Well, 3, 4, 5. 3 times 2 is 6. So is 4 times 2 12? No, they don't have a common multiplier. So this is not a triple. But we do know what A and B are. So we'll plug in what A is. A is 6, B is 12. And then we're just going to do algebra. 6 squared is 36. 12 squared is 144. And I cannot take the square root until I simplify this completely through addition. So then I get 180 equals c squared. Now my goal is to break this down, and I want to get the square root of 180 split up into really nice friendly pieces. Now you might know the largest perfect square that goes into this. But right away, I want to show you how I would do this and just see if you like it. I noticed 9 goes into this. Now I know it's not the largest one, so it's going to be a little bit of extra work. But the square root of 9 is 3. Well, then I can just look at 20, and a perfect square that goes into 20 is 4. 4 times 5. Well, then wait a minute. Isn't the square root of 4 2? And this is all multiplied together. So I get 3 times 2 times the square root of 5. But then 3 times 2 is 6. So that means if I wanted to pick a better number, the better option is what the square root of something gave me 6. That's 36. So 36 goes into 185 times, and that would have been the fastest way to get this done. But there is the length of the missing side. All right, so what happens if it looks a little bit different? What happens if one of my side lengths already has a square root in it, and I need to use that to find other missing sides? Well, in this case, we know the hypotenuse. That's the longest side across from the 90-degree angle. And I know another side. It doesn't matter if I call it A or B. But if I call one of the legs A, then the missing side is B. And because this is a right triangle, if I know two sides of a right triangle, the Pythagorean theorem will always help me find the other side. So we're going to plug in the hypotenuse. We're going to plug in what we called A, and the only thing left to find is B. Now this is a really friendly problem because the square root and the squared, those undo each other. So you know those are inverse operations. They're going to reduce out. And the square root of something squared is just itself. So that's where the 34 comes from. And I'll give you a second to get caught up here. But now it's just algebra. We just have to solve for B. So you take 34 minus 16. Notice I'm isolating the B squared. And then I just have to take the square root. But I want to think of this 18 as the square root of 9 times the square root of 2. So we're reducing that factor. And the square root of 9 ends up being 3. Times the square root of 2. Okay, so the very last one on this concept is it's set up the same way, but what happens if I have a 3 and a square root of 7? So I've got both the number and the radical. Now notice that is the longest side. It's across from the square root. And then it doesn't matter which one I call A or B, but I got to find the length of B. Now here's the part where a lot of students kind of make a tiny mistake. What are we doing? We're squaring the entire 3 square roots of 7. So here's the part where students make a mistake. Right away, they're like, ooh, cool, that square root and the squared reduce out. However, it's almost like the distributive property. I don't want to call it that, but you're basically saying everything inside of that parenthesis is going to be squared separately. So the 3 is squared. Well, we know that 3 squared and 3 squared is 9. And then the square root of 7 is squared, which reduces the square and square go away. So you're left with 7. And 7 times 3 is 63. So that's how this part all breaks down. And then that's equal to the right-handed side, which I don't have to keep writing that, but 3 squared is 9. And now it's the same work we did for the other two, is just get b by itself. So if I subtract 9, I'm left with 54. And then I want to break down that 54 into a large perfect square. So nothing pops out to me right away. Like I'm like, I don't know. And usually what I'll do is I'll take my calculator and I'll divide it by some pretty big squares. I might try 54 divided by 36. That's 1.5. That doesn't go in evenly. So I'm going to take the next biggest perfect square so instead of 36, I know 25 isn't going to work because it doesn't end in a 0 or a 5. So 25 isn't going to work, but what about 16? No, 16 doesn't work. Okay, well, 54 then divided by 9. Oh, hey, 9 times 6. And you might have seen that right away, but I wanted to show you my thought process when going through that. The square root of 9 is 3. Square root of 6 can't be broken down anymore. And there's the length of b. Now, sometimes you're going to get really friendly answers, but I wanted to show you the ones where you don't get friendly answers because those are the ones that are more challenging. All right. We've got one last concept to talk about, and the question is, we've used Pythagorean theorem because we knew that this was definitely a right triangle. But what if I have 3 side lengths and I'm not sure if it is a right triangle? Can we make other conclusions? What if a squared plus b squared doesn't equal c squared? What else can we decide and determine? So let me know if I'm moving too fast. These notes will be posted, and I'll put the video up. So we're going to do section 7.2 now, which is called the converse of the Pythagorean theorem. Well, converse just refers to switching around the if and the then statement. Let's think about that. The Pythagorean theorem said, if I have a right triangle, then c squared equals a squared plus b squared. What if I flip that around? What if I say that if I have 3 numbers and c squared equals a squared plus b squared, then what do you know about the triangle? Then it has to be a right triangle. So we're flipping the hypothesis and conclusion around today. You didn't have to write the learning target, but this is just the title for 7.2. And we're going to jump, for time's sake, into right here. Now, I don't want you to write the words, okay? And this sounds kind of silly. What I'd like you to do is I want you to title it, or you already wrote the converse of the Pythagorean theorem, but I want you to write what's in the boxes here. So here's what we're going to do. If I give you a list of 3 numbers, and the hypotenuse squared is equal to a squared plus b squared, then that means that you have a right triangle. Right? That's basically what the Pythagorean theorem is stating. It's just the converse of it. But what happens if it's not equal to? Okay? Now, again, don't write the words, but what if I have the a squared plus b squared is bigger than the c squared? So what if the number on the right-handed side is bigger than the number on the left? Well, that means that the triangle is acute, and I'm going to show you kind of a way to think of that here in a second. Um, Maybe I can kind of do it with the pictures here. So what if I have a triangle that looks like this? Let me change it just a little bit. So what if I have a triangle that looks like this, and we think that this was a right angle? But then when we check the side length A, so this side length A when squared and added the side length B when squared, these two end up being bigger than the third side. Well, what happens then is this third side isn't long enough. So notice, if this was a right triangle, it would have to be a 90-degree angle here, and C would have to be longer. But in this case, C is shorter, and if C is shorter, then A has to kind of move to it, and it changes this angle right here. Instead of being 90, it's less than 90. So then we have an acute angle right here. All right, so then you can probably guess what happens if C squared is bigger than A squared plus B squared. Now, there's an important reason. Notice how we wrote C on the left-handed side. If you do that, then the relationships that I'm going to show you will always be true. If C is on the left-handed side, here's the way my brain works. If it's a less than symbol, less than means less than 90, so it's acute. If C is greater than the other two sides squared, greater than is greater than 90, so that would refer to obtuse. And here's kind of a visual to get your brains thinking about it. What if C ended up being longer than A and B squared? Well, in that case, this point to match up would have to open up further, and you can see this angle that we wanted it to be right, but since C was longer, that ended up pushing this angle wider, and it makes it an obtuse angle instead of a 90-degree angle. Those are just some visual pieces that you can kind of think of it as. So, really quick, the only way that these relationships are true, equals is right. If you say less than, and less than referring to acute, the only way that's true is if you put C on this side. Because what happens if I wrote C on the other side? Then the inequality would open the other way, and it would contradict what we just talked about. So my little trick for learning only works if you say C is on the left-hand side. All right, so let's show you how this works. And let me know if again, if I'm moving too fast and you didn't get time to copy, I can give you an extra minute on this. We're not going to do all of these. Actually, we're not going to do any of those. Sorry. We're going to do these. These are better. All right. So notice the directions. Tell whether the given side lengths form acute, obtuse, or right. Well, that's where we're checking. In this relationship, we want to start with the hypotenuse first. So I'm checking how does c squared relate to a squared plus b squared? And notice how I didn't put an equal sign. I put a question mark. If c is on this hand side and we have a greater than symbol, then it's obtuse. If it's less than, then it's acute because the other two sides are larger than c squared. And if it's equal to, then it's a right. So those are the relationships we're looking for. But then the question you have to be careful with is, what is the c value? Right? C is always the hypotenuse. So we have to read the given numbers and indicate which one is c. C is the largest number. It doesn't matter which one I call a or b then. All right, so what we're going to do is set up that relationship. And we're just going to check. Notice I didn't put equals, I didn't put a symbol because that's my question. How does c relate to the other two sides squared? So let's just plug in what we know. How does 20 squared relate to 7 squared plus 18 squared? And then 20 squared is 400. 7 squared is 49. 18 squared is a big number that I'm going to cheat and use my calculator for. And then we can add these two together. Now I can determine the relationship. Well, what do we know? C squared ends up being larger than the other two sides squared. So if C is larger, that means it's going to open it up wider, and A and B have to basically open up further. So that means that this is end up being an obtuse triangle. Now, some of these you have to use your calculator for, and some of them you kind of do and don't. So I'd like you to try. Oh, we don't have a lot of time left. Um, why don't you guys do this? I want you to do the third one. I'm going to set this one up just so you can see it and we can talk about the answer, but I want you to try the third one right here. Go ahead and do that while I work on this one. Just, I guess the one thing I'll mention here, how do you know which one is C? Right? Is 11.4 bigger than 3 square roots of 10? Well, here's my hint. What if this was the square root of 9? Right? Square root of 9 is 3. This is 3 times 3. So 3 times 3, well, that's going to give me 9. So this number is bigger than 9, but is it bigger than 11? And if you're not sure, you can just take your calculator and do 3 times the square root of 10. And you get 9.486. 868, which we don't want the decimal answer, but I just want you to know that, okay, this number is smaller than 11, so that has to be the C value, and here's A and B. So now we know the correct C, but go ahead and you guys do that one. I'm going to work through this one. All right, let's take a look here. Let's go over the third one, and then I'll just quick talk about the middle one. So c squared is 11.4 squared is 129.96. And then remember, this one here, without a calculator, you can still figure out what this answer is pretty quickly. You're squaring each piece. Well, 3 squared is 9. The square root of 9 squared is 10, so 9 times 10 is 90. And I'm looking for how does c squared compare to a squared plus b squared? When I add these two together, I get 126. And you can see that right now, 129 is larger than 126. And since c was on the left-hand side, this is our obtuse triangle. Okay. If it was equal, then our conclusion is it would be a right triangle. And the middle one, you can see it was decimals, but the a squared plus b squared ended up being larger than the c squared, so that means we have an acute triangle. So I think you hopefully got the hang of that. You didn't need to write down all of these examples. All right, let me quick show you what we got for homework tonight, and then we'll turn you loose. So homework tonight is two parts. It's 7.1. 7.1 is only using Pythagorean theorem. So it's just getting used to that. Remember, we don't want decimal answers. The only time you can have a decimal answer is when you have a real life problem. So number 34 is the only one you should have a decimal answer for. Everything else is going to have the square roots in it. And then 7.2 is using that last piece, determining if it is right or if it's obtuse or acute. So I will be available from 1 to 2 through my office hours today. If you have any questions, you need any help, and then just make sure when you do this homework, you submit it to Schoology when you're done. Have a great day. Enjoy the sunshine.